Welcome to aminacademy.com. In fluid mechanics, let us discuss about method of determining the coefficient of viscosity, rotating cylinder method. Look at this figure. This method consists of two concentric cylinders, this one and this one, two concentric cylinders of radius R1 and R2 as shown in figure. The narrow space between the two cylinders is filled with a liquid whose viscosity is to be determined. The inner cylinder is held stationary by by means of a torsional spring, while outer cylinder is rotated at constant angular speed omega. The torque T acting on the inner cylinder is measured by the torsional spring. The torque on the inner cylinder must be equal and opposite to the torque applied on the outer cylinder. The torque applied on the outer cylinder is due to viscous resistance provided by liquid in an annular space and at the bottom of the inner cylinder. Omega is angular speed of the outer cylinder. Let omega equal speed of outer cylinder. Therefore, the torque applied tangential speed now tangential speed of the outer cylinder equal R2 omega. Tangential velocity of liquid layer in contact with outer cylinder will be equal to the tangential velocity of outer cylinder. Therefore, now velocity gradient over the radial distance over the radial distance R2 minus R1 is du by dy, which is equal omega R2 minus 0, the initial speed is 0 over dy is R2 minus R1. So which is equal omega 1 omega R2 omega R2 over R2 minus R1. Shear stress equal tau equal mu du by dy, which is equal mu into R2 omega R2 R2 minus R1. Shear force, therefore shear force F equal shear stress into annular area 2 pi R1H. That is this area. Two pi R1H. Therefore, next, the torque T1, on the inner cylinder due to shearing action of the liquid in the annular space is shear force into radius. Shear force mu omega R2 over R2 minus R1 into 2 pi R. 2 pi R1 H into R1. So, which is equal to mu 2 pi mu. Okay, I can write pi first. 2 pi mu omega H R1 squared R2 over R2 minus R1. And similarly, if the gap between the bottom of the cylinder is H, then the torque applied on inner cylinder, torque applied on inner cylinder T2 equal mu by 60T, already we proved, pi squared n r power 4. But you know that r equal to here r1 and thickness of is h we put, then T2 is equal mu over 60h, mu over 60 mu over 60h into pi squared n r power 4, pi squared n r power 4, r1 power 4. Therefore, total torque acting on the inner cylinder is equal T1 plus T2, both torque added. Therefore, T equal T1 plus T2, that is equal 2 pi mu omega h r1 squared r2 over r2 minus r1 plus, then T2 is pi mu omega then further T2 we can write, before that we are writing the then Then omega, we know that omega equal 2 pi n over 60, or we'll put n equal 60 omega over 2 pi. Then we have to substitute this n is 60 omega 2 pi, and this we can write T2 equal mu over 60h pi square. It is 60 omega over 2 pi R144. By simplification, we'll get pi mu omega over 2h R1 power 4. This T2 we are substituting here. That is now total torque acting inner cylinder is T1 plus T2. So we are having this one pi mu omega by 2h R1 power 4. So we are keeping the common factors, that is 2 pi mu R1 square common for this. After that, R2h over R2 minus R1 plus R1 power 4 over 4h into omega. So from this we can find mu equal 2 R2 minus R1 ht over pi R1 squared omega 4h into h R2 plus R1 squared R2 minus R1. Here this is a viscosity of the oil filled between two cylinders. And then here where T is the torque measured by the strain of a torsional spring. Therefore this both torque is equivalent to torque measured by the strain of the torsional spring. Then we'll do an example problem regarding this concept. A viscosity of liquid is determined by rotating cylinder method, in which case the inner cylinder of diameter 25 centimeter is stationary. The outer cylinder of diameter 25.4 centimeter contains the liquid of a height of 32 centimeter. The clearance of the bottom of the two cylinder is 0.6 centimeter. The outer cylinder is rotating 400 rpm. The torque registered on the torsion meter attached to the inner cylinder is 5.85 Newton meter. Find the viscosity of the fluid. Here we'll write the given things first. Here first the given things D1 inner cylinder diameter D1 equal 25 centimeter, which is equal 0.25 meter. Therefore from that R1 inner radius is 0.25 by 2 is 0.125 meter. Like that, outer cylinder D2 diameter is 25.4 centimeter, 25.4 centimeter, which is equal 0.254 meter. Therefore, outer radius R2 equals 0.254 over 2 equals 0.127. The height of the liquid from the bottom, height of liquid from bottom is 32 centimeter. 32 centimeter. Then H equal 0.6 centimeter, which is given therefore 0.006 meter. Here 0.32 meter. Then for H, the total height difference is 32 minus 32, that is 0.32 minus 0.006 meter, which is equal 31.4 meter. It is centimeter, then we will convert in meter, is 0.314 meter. Now speed of the cylinder n equal 400 rpm, revolution per minute. Then omega equal 2 pi into 400 by 60, which gives 41.88 radian per second. Radian per second. Then we'll get the torque, given torque applied is given 5.84, 8.85 Newton meter. Therefore, mu equal 2 R2 minus R1, the formula you're writing, HT over pi R squared omega 4 into H into H, R2 minus R2 plus R1 squared R2 minus R1. So we'll apply the values. Therefore, mu equal 2 into 0.127, that is R2. Then R1 is 0.125. H is 0.006 and T is 5.85 over pi into, that is 3.14 into 0.125 square into 41.88, that is this omega, then into 4 into H equal 0.314 into 0.006 0.006, then plus 0.125 square, that is R1 square, into 0.127 minus 0.125. So equal, then this top value, numerator value is 0.000 0.001404 over the bottom value is approximately 0.001, which gives 0.1404 Newton second per meter square. Multiply by 10 gives poise 1.404 poise. Therefore, viscosity of oil, viscosity required is 1.404 poise. We have done. Please subscribe our YouTube channel.